All right, hello everybody. In this video, we're going to talk about equilibrium in 3D. Up to this point, we talked about equilibrium in 2 dimensions, and we said we could have 3 unknowns, some of the forces x equals 0, some of the forces y equals 0, and some of the forces z equals 0. Well, this is the same thing in 3D, except now we're adding some additional equations. So we still have some of the forces in the x and y, but now we're adding some of the forces in the z, and we're setting them all equal to 0. We also have the fact that we can say that the sum of the moments about any point are equal to 0. Or in essence, what that means is if we were to sum up all of our r cross f's, we get those each have to be equal to 0. Which what that means is the moment about the x-axis is equal to 0, moment about the y-axis is equal, the moment about the z-axis is equal to 0. So what we end up with is 6 equations, so that we can have up to 6 unknowns and still be statically determinate. All right, so let's talk about a general process. All these problems can be solved in somewhat the same way, at least the general process that I tend to follow. The first step in my process is to resolve all of my forces into their I, J, and K components. After we have resolved them into components, then generally what I'll do is I'll sum the moments about some kind of point. Now the key to this part, to this step, the second step, is that you want to pick a point that contains 1 or 2 unknowns to make the problem solvable. So be strategic where you pick that point. Another point we need to point out is with this radial arm vector, you have to get your direction correct for that one, and it is going to be from, so we'll say, let's see, what do we want to say? We'll say vector r is from the point to the force, starting at the point that you're doing the moment about and going out to the force. You'll see that in just an example in case you don't know what I'm talking about. When we do our moment about a point, we end up with this whole matrix that we've seen before. And we're setting this whole thing equal to 0, and then we're finding the determinant, expanding it out. So let's see, find. When you find the determinant, you're actually going to have usually multiple forces. So you'll have multiple I hats, j hats, and k hats. So the third step to solve this is that we are going to set all of our I hat components from those determinants equal to 0, our j hats equal to 0, and our k hats equal to 0. And what this is in essence taking the moment about each axis and then solving for any unknowns within that. And like I just said, after we have that, solve for any unknowns, because that'll be 3 equations that you have here. You should be able to solve for 3 unknowns in this case. The last step is to solve for those other 3, and this will be based on whatever point you chose to take the moment about, because that would not give you any information about the vectors, the force components at that point. So the last step is that you want to set some of your forces in the x direction equals 0, some of the forces in the y equals 0, and some of the forces in the z equals 0 for your other 3. So I think this can best be seen in an example. So let's take. Okay, so here's our example. What I have is this boom sitting out with attached at A with some kind of pinned connection, and then I have C pushing down with 840 pounds. I have 2 different cables holding it up. I have tension in BE, and I also have another tension in BD. And we said the first step was to put these forces into component form. So I kind of jumped ahead because that should be review on how to put them into component form. You start by finding the length of each one of these cables, and then to put them in component form, you're taking the magnitude in the x direction divided by the hypotenuse, magnitude in the y over the hypotenuse, magnitude z in the hypotenuse, leaving these as variables because we don't know what they are, to find our tensions. Also with this, don't forget your 840 pound external force also needs to be put into component form. The next step is to identify any other forces or reactions at point A. I do have it's like a pinned connection. I can have an AX or ball and socket, I think is the way we looked on that little handout we had. AY and AZ. No moments at A, but I can have all three of those forces. It can support all three of those forces. So the next step, step 2, we said was to sum the moments about a point that will make many of these unknowns go away to solve what you're solving for. I'm going to pick point A, and I went ahead and drew in the all of my R cross F's. The way it works, as a reminder, is we're going from the point we're doing the moment about, from A, out to our forces. So I have the radial arm going from A to B would correspond to both of my tensile forces, and then so cross product with both those tensile forces. My second radius I need to look at is the radius going all the way from A to C, and that's crossed with the force at C, that 840-pound vertical force. So the next step is to set up those matrices. So bam, just like that. And with those matrices, you can see what I'm doing is for the R vector, because it's R cross F, for say this first one, what I'm doing is I only have from A to B is 6 in the X direction, 0 in the Y, 0 in the K, and then I'm taking my vector up here in component form for my I, J, and K, and doing the same thing with all three of the forces. So I have the two tensions for the first two, and then the last one is that 840-pound force straight down. I'm setting the whole thing equal to 0. So when I expand these things, which everyone should know how to do by now, or find the determinant of them, I end up with something that looks like this. So after I have the determinant and expand it, the third step in our process was to set all of our unit vectors equal to 0, meaning I'm adding up all my I hats from those three different parentheses, all my J hats, and all my K hats. Now if I look, all I have is a J and a K, a J and a K, and a K. So I don't really have any I hats. There's nothing to add. But if I look at my J hats, I have minus 36 over 11 TBD from the first set of parentheses. Then I have plus 36 over 11 TBE from the second. Must be equal to 0. So what that tells us is that TBE must be equal to TBD. The two tensions have to be equal. And you might be able to even rationalize that just by looking at it and see that it's symmetric and the cables are the same distances away, and so they have to be the same, but it's good to verify anyways. From our K direction, adding up those, what I end up with is this 42 over 11 TBD plus another 42 over 11 TBE, and I have minus this 8400 is equal to 0. So of course TBD and TBE are the same, so I can solve that, and what I find out is TBD is equal to TBE, but they're both equal to 1100 pounds. So the way I would solve it is I would just, oh, why isn't this working? There we go. The way I'd solve this is I would just make BE BD and then have 84 over 11 and solve for it that way. The fourth step in this process is that since we did our moments about point A, we didn't find any of the reactions at A. To find the reactions at A, we're going back to the sum of the forces in the X and Y and Z equal to 0. So starting with the X direction, I know I have AX is my unknown. That's pointing, in this positive X direction. And then I have these two tensions, and I'm looking at their X component. So I can either come back up to here and say that, hey, I know that their X component is minus 6/11, or I can look at their I hats and whatever works for you. So and I'm going to put in their values. So I have minus this 1100 times 6/11, and that's true for both cables. So I'm going to have the exact same thing again. Set the whole thing equal to 0, and I get a reaction at A in the X direction of 1200 pounds. Same idea in the Y direction. So sum of the forces in the Y equals 0. I have AY plus this 1100 times 7/11 plus the other cable has another 1100 times 7/11 for their components. Minus, don't forget this external force of 840. Set the whole thing equal to 0. And I get an AY equal to negative 560 pounds. You might want to ask yourself, what does negative mean? Does that mean I did something wrong? Does it make sense to be negative? So if I look up here, I assumed it to be positive with this AX, but actually it's pointing down, or sorry, AY, but it's actually pointing down. And that should make sense, because if we're pulling up here with this B and we're pulling down with this 840, you can imagine this whole boom wants to like rotate around, right? So AY needs to be the counteracting force on like a seesaw trying to hold it down. So it does make sense that it would be negative. Always good to check and not just trust your numbers, right? So that's some of the forces in the Y. The last one is some of the forces in the Z direction equals 0. AZ plus this 1100 times 6 over 11 minus 1100 times 6 over 11 is equal to 0, or in essence AZ is equal to 0. And you might want to ask yourself again, does that make sense? And if we have our two cables are the same magnitudes and they're both pulling in the X direction, or the Z direction, the same amount, right? So you can think of, one's pulling it this way, one's pulling it that way, but they're the same amount because they have the same ratios. And so yeah, it kind of makes sense that C would be 0. There's nothing else in that Z direction. So that's the end of that example. I hope you found it helpful, and we'll talk to you all soon. Thanks.